colleagues, I'm glad to see you here, and some of them who came by this vacation, I mean the weekends, so maybe the time is not very convenient, but still we are continuing now its normal workshop day, and I'm glad to know that today again Rein gave his acknowledgement to deliver his wonderful talk, and so we have something like 1 hour, and then later we have some break, and you can consult the schedule that is on the whiteboard. So the recent version of the schedule is there. So please, Rein, the floor is yours, and we cordially welcome you.
Okay, thank you very much. I keep the door open or closed?
You can close it. Maybe it's better.
Okay, good morning everybody. I'm very glad to see quite some people, as we say, like this one, not as many as yesterday, but there were more students, of course. It's also Saturday, so maybe it's more difficult for some people to come. I get this stick. This talk is completely different from the talk I gave yesterday. The topic is completely different, but also this talk is much more technical. Yesterday I gave a kind of tutorial introduction into Markov position theory. This is no tutorial. This is just pure technique. The techniques we use there are probability generating functions, and I will show that sometimes it's quite difficult to find these generating functions. But first let me sketch the environment, the model. And maybe it's nice to start with some application. When I did this talk also in Moscow, and then I said, well, we came from the airport, and also Alexander Dudin and Krishnamurti came from the airport, only they came 2 hours earlier than we came there. And they arrived maybe 50 minutes from the airport to the hotel, and we arrived 2 hours later, and even it was Sunday, we took us about 2 hours to arrive. So you have the phenomenon of rush hours. Even near Moscow on Sunday you have rush hour. So that's an example of a random environment. Some times of the day the traffic is rather light, and other times of the day you have very heavy traffic. So light and heavy traffic can be expressed, of course, in cubic terms as the arrival rate. So let me just take as an example. You can say, well, when there is no rush hour, we have an arrival rate of lambda, and when there is rush hour, we have an arrival rate of lambda 1, and lambda 1 is much larger than lambda 0. That's everybody can imagine such a situation. And maybe this is 80% of the time, and maybe this is only 20% of the time. So then when you want to build a toll booth, for instance, you want to build a toll booth, you know, cars arrive and you have to pay some money for access on the highway. What you would do maybe is something saying, well, I want to take the average arrival rate, which will be then 0.8 times lambda 0 plus 0.2 times lambda 1. And I just, for instance, when I want to make a design for the number of lanes in front of the toll booth, I say, well, I take this as the overall average arrival rate, and now I study a queuing model with this arrival rate, and then I can calculate all the performance measures, and once I know these performance measures, I have an idea of how many lanes I need in front of this toll booth. The idea of this talk is to show that approach is very false, because it underestimates this effect of a random environment. So the message which I want to bring through, and I will repeat it during the coming hour several times, is that just taking a weighted average of the different arrival rates and then study a model with this arriving rate leads to performance measures which have nothing to do, to say it a little bit exaggerated, with the real performance measures of the model, in which really 80% of the time you have this arrival rate and 20% of the time you have this arrival rate. And this environment, so you can say this is rush hour, and this is quiet periods, quiet. So taking this average just leads to wrong answers. That is the idea of the result of this research, and that has maybe found already by other people. But, and then comes the second part of the title, I wanted to study this in discrete time, because everybody knows nowadays with modern communication systems, discrete time models are very, very important. And in computer communication, you have the same problem, of course. You have periods that many people want to approach a certain website, and they have kind of rush hour, and you have other periods that nobody is looking at that website. So you have the same phenomenon everywhere. And just taking the average arrival rate, that is a wrong approach. That's the message. So then we have to show that. But first I want to say that this is joint work with a student, my student Annette Ronda. She wrote a master thesis, not a PhD thesis, but she wrote a master thesis on this model. And she did the numerical work. Mostly she also checked all the mathematics which I had calculated before. And so everything was double checked. And also she wrote a simulation program to check that the numerical results were really correct. So we have double checking that the results are correct. Okay. Of course everybody knows I'm at Vrije University and she's a student services is in the same place. So we talk about the discrete time queuing model in a random environment, and we have one server, so one toll booth or one website or whatever. Next please. So in outline I will describe the model. So from now on I will not talk about applications anymore. I've spent time enough, I think, for this audience on the application, and I want to give a full description of a model which is LASDARE. I say already now that what it stands for. It is so-called a late arrival system. Later I will explain what that means. This is called delayed access. Many people know what that means, and this stands for random environment. So I will start with a full description of the model. Then we give a Markov chain analysis of that model. So we will give a steady state analysis of this random environment model. What does it mean? Of course, we want to get all the information at the distribution level in forms of probability generating functions, and you'll see that the dimension of the state space is 3, because you have a number in the queue, you have so-called residual service time, it's a so-called supplementary variable technique, and of course you have the environment. So in principle it's a three-dimensional state space. From the full analysis, we can, by marginal analysis, we get the queue size distribution, of course always in terms of the probability generating function, but we know that we know everything. We look at the individual waiting time. Individual is important here because in my model you will see that batches arrive. So it's a batch arrival model. In a toll booth, whole groups of queues of cars can arrive at the same moment. For instance, at the traffic light, you have a whole bunch of queues waiting, then the light goes green, and then the whole batch arrives at that moment. So batch arrivals is a very convenient way here. And then of course you have to ask yourself, what is the waiting time of the individual customer, because this customer is somewhere in his batch, and that gives more complications. Once we have given all this, we give numerical results. And what is the main importance of these numerical results? Not these numbers in themselves. Like I said yesterday, we want to get qualitative insights from numbers, not the numbers themselves. We want to show that when we compare this random environment model with the standard model, and what is the standard model? The standard model is that you have just one arrival rate. So in continuous terms, because you're more acquainted with this, if you have Poisson streams like here, lambda 0 and lambda 1, and this is the environment situation, 80% quiet period, 20% rush hour. Taking this, and then you get a much more simple model, because then you have only one Poisson stream. Then you get, we want to compare the results of that model. So we call that the standard model with the mixed batch arrival distribution. Okay? Because now, that will be clear, in one environment, the batch sizes which arrive are stochastically much larger than in another environment. Yeah? And then we come to some conclusions. Okay, that's good. So first, for people who don't work very much or have not worked much in discrete time, time is only discussed in discrete terms. So we talk about time slots. You can think of a small time unit, and in that time unit, everything has to happen. I have a picture of that later, so we will make a picture on the board. So physically, you can look at it as a time unit. Arrivals at time epoch k physically occur during time slot k. So I'll make this nice here. Make some picture. So I have here. So this is some time slot. Call it time slot k. Then arrivals arrive here. That's the arrival. A service starting at time k always starts at the beginning start of the service. If there is a start of the service, of course we have only one server, so it's not that every time you start with the service. So, but this is the situation. And a departure at time t physically occurs at the end. So here we have departure epoch. So it's possible in principle that in one time slot all three events happen. There can be the start of a service. If that service time lasts only one time slot, then we also have a departure at the end. And we have arrivals during. What is the consequence of this setup? That when there is a departure at k, then an arrival at k sees the server busy even if the queue is empty. And that's what we call late arrival setup. Other people usually study early arrival setup. I came up with late arrival setup when I started studying discrete time models or retrial models. Then I thought that late arrival setup is more natural, but almost everybody in the world disagrees with me about this fact. So I'm the only one here who believes that. He takes this choice. Okay. And now, of course, we have also a change of the environment, which is possible, and that takes place after a departure. So that's the setup. And then, of course, the next question is, what is our point of observation? So next slide, please. First, I explain this delayed access. If you arrive at time k, so we arrive here, your service can start only at time k plus 1. So not immediately. That's also very important to notice, of course. This late arrival, as I explained here already, we can also pronounce it as arrivals have precedence over departures. That's the same as late arrival, but this is maybe less clear than this picture. We have the random environments. Departures have precedence over a change of the environment. So when we have a departure, only after that departure, in the same time slot, we can have a change of the environment. Of course, I must specify how the environment changes, but that comes later. Yeah? Okay, next slide. So here's a picture. This is a picture made by Annette, because I don't make so many pictures. This is a very nice picture. Normally I don't have this picture, I always do it like this. But here you can see it very clearly. She talked about t, I normally use k, okay? So here you have time slot k minus 1. Here you have time slot t, and here you have time slot t plus 1. So she concentrated on what can happen in time slot at, we can just say at time t. In discrete terms, at time t. So if there is a start of the service at time t, you see it here, arrivals during, departures here, change of environment here, that's what I said also there, and we look at the system here, just after a possible start of the service. That's our observation point. And we want to study the model. Of course, I must describe the model at these points. So we embed, so see it later, we will embed a Markov chain at these observation points.
But is there, sorry, Rein, is there any difference? I mean, if you switch this observation point to something like after...
Well, it's important that you look at a certain point when the arrivals at the same epoch still have to occur.
But I mean,
we will see that when we go a little bit into detail when I will explain the balance equation.
Okay.
Of course, if I make the point of observation after a departure, then it's completely different because then the arrivals have occurred already.
Yeah.
And so you put yourself at a physical time point just after, possibly, and it's not necessary that time t a service starts, but it's possible that the service starts. Immediately after that, you start to look. Before any arrival, possible arrival, it's also possible that no arrivals occur, but before any possible arrivals, and a possible departure, and a possible change of the environment. Yeah? Okay, so that's next. So now we start with the description of the model. Anytime the environment is in one of two states. So here in my example, quiet and rush hour. So I call these environments 0 or 1. So when you are in a certain time point, either the environment is 0 or the environment is 1. Now comes an important one. How long is the duration of a given environment? Well, with probability pi, the environment changes from environment state I into 1 minus I. So, the duration of environment 0, is geometrically distributed with parameter P0. The duration of environment 1 is geometrically distributed with parameter P1. In Moscow, somebody asked me, they thought that P0 plus P1 should be 1. No, why? It's just two different geometrically distributed periods. So you can take one, maybe 1 over 25, and the other 140, or something like that. So it's not necessary that they sum to 1. But two independent geometrically distributed. But you can imagine now, you just arrived in a certain environment, you throw a coin with the probability P0 of heads, and every time slot you do that, and when you finally have heads, then the next time slot will be in the other environment. And that alternates between 0 and 1, 0, 1, etc., etc. Yeah? So here I say the southern time in environment state I is geometrically distributed with parameter Pi, and I is 0 or 1. In every time slot, customers arrive in batches. As I said already, groups arrive. Of course, then we must know the distribution of the batch size. And the batch size distribution depends on the environment. Of course, something must change. So that's why my example with cars entering a highway after a traffic light, random batches arrive at the toll booth. And during rush hour, these batches are stochastically larger than during quiet periods. But there are batches. But of course, at the toll booth, every car has to be served individually. So you have batch arrivals and individual service. Yeah? So that's the important remark here. The batch size arrival distribution depends on the environment. So here I describe it's generally distributed. In environment state I, the batch size arrival distribution is just AK, the superscript I. So this is the probability that at a given time slot, when the system is, given that the system is in environment I, K cars arrive. And when I is 0, you have a different distribution. And with respect to the service time, okay, no, the service time is on the next slide. Here I have the generating functions. So the generating functions, there are two generating functions because they are subscripted by the environment index. So I have an A0Z and I have an A1Z. So two different batch size distributions. Okay, next one. Each customer requires a generally distributed service time. The service times are the same. Alexander Dooley made a remark about this. He said, well, you can also change the service time. Except if you have a toll booth, what's the service time? That's the time you need to pay your money. So that is not dependent on the environment. Maybe you can also imagine examples in which also the service time is dependent on the other. But to keep it simple, I only change the arrival distribution. And I keep the service distribution constant. But the distribution is general. So here we have Bj. That is just the probability that an individual customer, an individual car, needs J time slots for its service. And we have the generating function B, and I go use here W. Okay, well, I think that's quite clear. Then, of course, very important, there's one server. We're mathematicians, so we have solutions. If you take many servers, things will become very, very nasty. So one server, and of course, unlimited waiting space. That's always a little bit paradox that unlimited waiting space is normally easier to analyze than a finite waiting space. Yes?
Sorry. So when a customer arrives, the server is not busy but idle. So does it mean that it can start only the next slot?
Yes, the server can only start there, but here the last sentence I didn't read yet. Customers who on arrival find the server busy are placed in a queue. So it's no retrial queue, it's just you are in the queue. But of course, if you arrive at an empty system, so if you arrive, but your batch arrives in an empty system at time 7, then at time slot 8, the first customer of that batch will start his service. But when you have the 9th position, of course, you still a very positive waiting time. Yes? So that is just a queuing one. But the environment changes in this way. Next. So now we start here, steady state analysis of this model. I hope the model is clear. Any questions about the model? Confusion? Clear. Very clear. Very clear. Okay. Okay. So I said already in the beginning, I will use the so-called supplementary variable technique. I didn't use that word here, but I keep track of the residual service time of the customer in service at time k minus. This k minus is our observation point. I call it k minus. You can criticize it. Some people say, well, why do you use k minus? Also, Annette herself came to me and said, well, you said, no, Mr. Nobel, why do you say k minus, etc. You can call it k minus plus or whatever. You can make a very complex notation for it, but we mean the observation point. Qk is the number of customers in the queue, excluding the possible the customer who is in service, only the queue, right? And of course we have a random variable with value 0 and 1, which stays for the environment. So we have these 3 random variables. And
yeah, sorry. So once again, to clear this out, so it could be like this. HK could be 0, but QK could be less or more than 0, because someone is standing in the queue. He just arrived, the batch arrived, and then the service is empty, so there is nobody served. So at some specific k minus, it could happen. Yeah.
Yeah.
Okay.
Yeah. Okay. So here we have this 3-dimensional states description, and that is a irreducible, aperiodic, discrete time market chain. Of course, that's quite true. Maybe you can find some specific batch size distributions that it's not aperiodic or so. What is the traffic intensity, the stability condition? Well, here is the B prime 1, of course, is the mean service time. And here you have the mean pressure. This, what is written here, is our Laplace star. Yeah. Of course, because you have maybe for, I don't know, of course, you're all scientists, so maybe it's not necessary to do it, but you have 1 over P0, and here 1 over P0 plus 1 over P1. That's the fraction of time that you are in environment 0. And that gives P1 over P2 times this So you have the 0 here and the P1 there. At first sight it's a little bit strange, but that's because of course you have the reciprocal of the parameter. So this is the mean arrival rate. That is really this bubble star. But we will analyze this model in such a way that we include this change in the environment. So we don't take simply this as the mean batch size. Yeah? So of course that should be smaller than 1. Yes? Okay, next one. Now we start defining our limiting distribution, of course the joint distribution. I could have written the I also here, but I prefer to take the I as an index here. The I stands for the environment, the J stands for the residual service time, and the N stands for the number of customers in the queue. So, and then this is just the limiting distribution, so we take K goes to infinity and minus 0. So this is the limiting distribution. And actually it's 3-dimensional, but we will analyze it because these have only values 0 and 1. We can analyze more or less the 2-dimensional case, and then we just have to, everything, you can switch I from 0 to 1 and vice versa, so that's not a problem. So here is the 2-dimensional, let's call it like this, 2-dimensional generating function of this model, and of course defined in this way. And our main goal is to calculate, to find the formula for this generating function. That is our main goal. Once we have this, we can find also the generating function of the queue length, and we can find the generating function of the individual waiting time. Okay. So first, you're used to that, of course, you take a very detailed look at the model, then you find everything, and then by marginalization, you find your performance measures. Doing the analysis, we also need what I call partial one-dimensional generating functions. So we have the I is again the environment, the J is this residual service time. So I fix the J now, and I just sum over the N. So that's these quantities will occur, of course, during our calculations. So I hope everybody can understand what this means. So next. So we start now with the balance equation. And because we have some time, I think it's always nice to explain the balance equation, because once you understand the balance equation, you understand the model. If you don't understand the balance equations, then you don't understand the model. So we start with a very simple situation that the system is empty, and we are in environment I. How can you arrive in this state? Well, of course, it's possible that you were already in that state. There were no arrivals in that time slot, in the previous time slot, and there is no change of environment. Or, the other possibility, the residual service time is just 1, no arrivals, no change of environment, and of course then you also end up in this state. So the first term here refers to the situation that the environment does not change. But of course it's possible that the environment changes. So we were in the last epoch, the system was also empty, but we were in environment 1 minus I. No arrival, you see here this precedence that arrivals come before the change of the environment. No arrivals in the original environment, but then a change of environment, so then you end up here. Or residual service time 1, and the same. So this is the simple balance equation for the empty state. So now we go next slide to the general balance situation. So we take the probability that you are in environment I, residual service time I, and number of customers in the queue N. How can you arrive in this situation? But the previous epoch, the residual service time was J plus 1, no change in environment. And of course then during that previous epoch, we had some arrivals belonging to that environment. So here maybe there were N minus K, but when you have K arrivals, then you end up with N. So this is one situation. And here you have the same situation, but for the for the fact, the possibility that the environment changes. So these are the simple ones. The more complicated ones are here. They refer to two possibilities. Either that the residual service time is 1. There are n plus 1 minus k in the queue, and k arrive, and there's no change of environment. And the service time of the customer who now goes into service, that's the first one in the queue, if there was a queue, is j. And then you arrive at it. Or, that's the other one, the system was empty, no change of environment, and n plus 1 customers arrive. Because then in the next epoch, time slot, one of these customers, the first one of the batch, will start its service, and it probably be j. This service will last j time slots. Okay? Maybe I'm too detailed, but I think when I hear all these things, sometimes when I see all these equations, I don't really understand. And this is the same situation, but for the change of environment. So, from this balance equation, the balance equation from the previous slide and from this slide, we have to construct our generating function. So next slide, usual way, we multiply by z to the power n and we sum over the n. So then we get this partial generating function. Okay, now I don't go into the details here, that doesn't make sense. But you find something like this. You see already quite complicated. You see here pi I1 0 and A0I is we can get rid of that using the previous, the first balance equation, and then we can rewrite this expression for this partial generating function. So to get the full generating function, once we have this one, we have to multiply by w to the power j and sum over the j. So this, okay, I repeat, I don't go into detail here. This you see is rather complex. And you see, you have this is unknown function, of course. Here you see this function for environment I. Here you see it for environment 1 minus I. You see also the different second index, etc. So next. So multiplying by w to the power j, summing, we get this. And now we can look at this formula. Here we see one of the generating functions we want to find, and here we see the other one. So we have these two functions, but you must realize that these are two equations, because I can plug in a 0 here, and I can plug in a 1. So this is two equations. This illustrates these are two equations. When you look closer at this equation, you see several unknowns. Of course, these are the unknowns, but that's our goal. But there are other unknowns, and these other unknowns are these probabilities that the system is empty, either in environment 0 or in environment 1. So these are two numbers. These are numbers. We know that the sum of them is 1 minus rho, because this is simply the fraction of time that the system is empty, so that is 1 minus rho. So we have one equation. But what is lacking is a second equation to solve, to find the numerical values of these probabilities. And the other unknowns in this part are these partial generating function pi 0, 1, z and pi 1, z. So we have 4 unknowns. And we have here 2 equations. So we have 2 equations, and we have here 1 equation. So we have 3 equations and 4 unknowns. So there is a problem. Yeah? Okay, next. I can get rid of the pi I1 wz by taking these 2 equations and get rid of the pi 1. And then I have something like here, only the pi 0 wz, then some rather complex coefficients, and on the right hand side only our unknowns pi 0, 0, here we have pi 1, 0, 0, these are the 2 unknown numbers until now, and we have these 2 unknown partial generating functions pi 0, 1z and pi 1, 1z. So all at the right-hand side, those 4 unknowns, of which 2 are numbers and 2 are functions. So we have 2 unknown numbers and we have 2 unknown functions. And we have only 3 equations. Yes? So, how to continue? Well, if you look at this coefficient, here's a factor z, but I take only the expression between brackets, you see that is a quadratic equation in W. Go to the next slide, please. Consider the coefficient on the left-hand side. This is a quadratic expression in W. Here is, this expression is spelled out. So what we do, we consider the roots of this quadratic equation. For every z, we get roots, and the roots are here. It's just the solution of a quadratic equation, where these roots are functions of z. But now, in the previous slide, please. When I plug in these roots for w in the right-hand side, the whole right-hand side becomes 0. And I have 2 possibilities. I can plug in the root, which I call w plus, and I can also plug in the other root, which is w minus. So then I have 2 equations. Okay, next. So that's what I did here. So here's the solution. This is the discriminant just, and the discriminant has a nice form. Here you can see it as a square plus something. We take a technical assumption that here 1 minus pi 0 minus pi 1, that this is always positive. That's necessary in the analysis. This is a technical assumption. Okay, so next. Choosing w, either w plus or w minus, the left-hand side of this previous equation, we get 2 equations for the 4 unknowns. So again, 4 unknowns, we had already pi 0, 0 plus pi 1, 0, 0 is 1 minus rho, that was 1 equation, and now we have 2 more. Still, 1 equation is missing before we can solve the situation. Now I will skip a little bit the technical details. I use some abbreviations. So now we do a lot of calculations. So next slide. Next slide. Next slide. Oh, sorry. No. Okay. When I do a lot of calculations, one of these unknown partial functions can be expressed in this way. Here you see all these abbreviations. So we had to work out all this in detail. So go to the next slide. We first evaluate the denominator, we get some results. Next, we evaluate the numerator, we get some result. Next, and now here, this is one of our 4 unknowns. This is one of the 2 unknown functions. And now we have written this unknown function as a fraction, a rational expression. This is the numerator. And this is the denominator. And now we look at the denominator. First there's this minus sign. Here you see this 1 minus p0 minus p1. When this would be 0, then I get problems. So we assume, technical assumption, that this is. Also, when this is 0, what does it mean? Then pi 0 plus pi 1 is really 1. So then you change to often. Here we see the generating function of the arrival distribution in environment 0. Of course, I can write down also pi everywhere when there is a 0, I can write a 1. And then I have the same kind of expression. Here we see the generating function of the surface time in the point which is this w plus minus z. This is very easy to see. It's always positive. This one, when you take 1, it's negative, because this, I will see it on the next slide, this root is smaller than 1. When z is 1. Actually, it's 1 minus p0, 1 minus p1. So this is negative for z is 1, and it's positive for z is 0. Because when z is 0, this is still a positive root. So this factor has a 0 in the real interval 0, 1. And that is the key to our solution. Because we can look at this expression. Go to the next slide, please. First some facts. Okay, I don't go into details. I said already this one is that. When you take 1, for that one, both numerator and denominator are vanish. Both roots are always positive. We assume this fact, I said already. The denominator is negative for 0. This factor is always positive, and this factor is positive for 0 and negative for 1. So this factor is the key factor in the whole analysis. We have the generating function of the service time, and we plugged in the, let's say, not the negative root, but the root with the minus sign before in front of the discriminant, and that has a real 0, a real index in the interval of 0, 1. Okay, next. So the denominator, what I said, has a 0 and 0, 1. Call it z dot. So this is the solution of this equation. Okay? When you plug in that, maybe we can go back 3 slides. 1, 2. Yeah? No, sorry. Next? Yeah, this one. When we plug in the z dot here, then this vanishes. But this is a partial generating function, which has a positive value for z dot. That means that this expression must vanish also for z dot. And this gives us the extra equation. So next. So when we plug this in, we get this expression for the numerator. Next. So we get the following second equation for the numbers pi 0, 0 and pi 1, 0. And that is this equation. When you talk about. And once you have this equation, so this is a number which you can find numerically very, very easily. You have this equation, well, here's some technical remark, let's forget about this. We have this equation, now next. So, because we knew already that the sum of these was 1 minus rho, we have 2 equations for 2 unknown numbers, and we can write down this equation and find finally explicit expression for the probability that the system is empty in environment 0 and the probability that the system is empty in environment 1. Now these are the expressions. It's rather complex because you have the z dot, of course, which occurs, and you have these roots, which were the roots of that quadratic equation. Once you have this, so here's written down what these roots are. Next. We can take alternative, you can change the 1 into the 0, etc., etc. Then you have alternative expressions, but these of course have the same value. Next. Now we are done. In that sense, I can write down now an expression for this partial generating function, because the unknown numbers have been calculated now. And now here everything is known. But you see, this partial generating function is already a very complex expression. But now we are done, because we just have to change the 1 into the 0 and make all the changes. And so next, we have now the possibility to write down the full generating function. And here is the expression. Here are the numbers we know now. But here you see, still I didn't spell them out. These partial generating functions I left in this form. I'll go please to the previous slide. This is the expression for that. But of course I didn't expand that. Next. So this is our result. And just by changing 0 into 1, etc., we find also the other one. So we end here for this moment with a completely similar formula you can find for pi 1 WZ by interchanging the environment index from 0 to 1 and vice versa throughout the expression line. Next. So now we are done. We have expressions, but very complex expressions. So now the first step we want to analyze is the Q size distribution. So the Q size, the QZ is just plugging in 1 for the W and just sum these. That is the Q size distribution. And here is the expression. But you see in that expression, again, you have this very complicated partial generating functions. These are no known numbers, but these are still very complex expressions. So what do you usually do when you have found the generating function of the Q-size distribution, you start to differentiate, plug in one, maybe you use l'Hopital for a few times, and then you have the mean Q length. But, of course, it's out of the question, or maybe not out of the question, but when you send maybe somebody to Siberia for 10 years, then he can, and you say, well, now start to differentiate that, maybe after 10 years he can come back and finish his job. We didn't even try to differentiate this manually. Somebody suggested to use Mathematica or so, but I don't believe very much that you can plug in these type of things. It's too complex. So we took advantage of a very important numerical technique, which is the discrete fast Fourier transform. And it's very easy to plug in this expression in a MATLAB program, or nowadays Python, and just call the discrete fast Fourier transformation, and then you find the probabilities immediately. And that goes very fast. So that's what we will do when I come to the numerical results. Okay, next. Well, now, a few words. What's time?
15 minutes.
15 minutes, okay. The individual waiting time. Well, we can look at the generating function of the individual waiting time, just defined by this. We must make some agreement on the fact that when you arrive, the epoch in which you arrive is not counted as waiting time. So when you arrive at an empty system, your waiting time is not 1 because you have this delayed exit, but we call the waiting time, we define the waiting time as 0. So here, this is this remark, for the waiting time we don't count the slot in which the customer arrives, although we use the setup of delayed exits. So that's just a choice. That's good. Now, we do this by conditioning. Here, I have this probability that the tagged customer, so now you take one customer in mind, he is in some batch, of course he has some position in his batch, so this is the probability that the customer has the m plus first position in his batch and arrives in an environment state I, finds a residual service time j, and an ongoing service, and he finds n customers already waiting. This probability can be calculated. I will not go into the details here, but this is the answer. This is rather simple. This is, well, for a master student, this should be an easy exercise. So these probabilities can be calculated. Next. Then the probability that the waiting time of an individual customer is R, you just sum over all the possibilities, etc., etc. So I don't go into further details here. Let's go to the next one. You can change that into the generating function. And what you find is interesting, because here are all of them. And here you see again the full generating function which we found. And that was the main part of the whole talk. Finding these generating functions. We have given a very detailed analysis of the model, resulting in explicit expressions for these functions, and these functions are used subsequently for expressing the Q-size distribution and for expressing the waiting time distribution, at least at the level of a generating function. Again, here you see this was already a very complex expression, so it's also out of the question to take the derivative here. So the individual waiting times, the probabilities of the probability that the waiting time is R, are calculated by using this discrete fast Fourier transform again. Okay, next. So now, what I came in the beginning, I said, well, you have rush hour, you have quiet periods. Why not take the weighted average, lambda star? So that's what we're going to do now. So we look now at easier results for the standard late arrival setup model with delayed access. When there is then only one arrival batch distribution called the distribution AZ, then we have these. This is the generating function. This is the long run average Q length. This looks at the Poisson formula in discrete terms. And here you have the waiting time just distribution at the generation as expressed as a generating function. And here you have the mean waiting time of an individual customer. And of course you see that little helps. So this is standard. This is for more or less in Brunel's book, in a book of 93. But we did it all over again. I did it also many years ago already. But I do it a little bit different than Brunel does it. But these are the results. So what we can do is we can say, well, next, because differentiating what I said before, these generating functions of our model, the random environment model, is very cumbersome, too cumbersome. We use the discrete fast Fourier transform to calculate the long-run average mean Q length as follows. You can calculate the tail probabilities, both of the Q length and of the individual waiting time, and just to sum the Q length, the tail probabilities, because everybody knows from undergraduate probability that the sum of the tail probabilities is the mean. And now you can take 100,000 points in your discrete fast Fourier transform, so we get very precise results for that. So, although it's not possible to make explicit differentiation of the Q size generating function, we nevertheless can find very precise results for the mean Q length using this discrete fast Fourier. And we can, the same can be said about the mean waiting time. We check these things numerically, and we check that Little's law is still holds. So our numerical results are very, and I said already before, we also wrote a simulation program. Next. So now numerical results. We take the rho, which is just the traffic intensity. This is the mean batch size, whether you look at the random environment model or at the standard model with this mean batch size. So we take now two models, the standard model with this mean batch size and mean service time always 3, and we take a specific choice for our pi 0 and our pi 1, and you see the sum is not 0, and is not 1. Okay? So we want to compare the results for the mean Q length and the mean waiting time between the standard model, where we take this mixture. Yeah, so we take the lambda star, just the standard model with the mean arrival rate the same as the mean arrival rate in the random environment model. And we will see that we get differences. So I call that the standard model with a mixed batch size distribution. Yes, next. Let's first look at this standard model. So we take as the generating function of the batch size in the standard model just this weighted average. So at the distribution level, you take the mixture. Not only at the mean. Here I talked only about the arrival rates. I didn't talk about distributions. No, at the distributional level, we take the mixture. So very deep. So we go as close as possible with our standard model. We try to approach the random environment model. Because at distributional level, it's nearly the same, but it's different. So then we get these results in the standard model, Q bar and W bar. Next. What we do now is we vary, here I miss a prime, we vary the mean batch size in environment 0 and the mean batch size in environment 1. But the total average batch size remains constant. And we take, again, rather different values for the P0 and the P1. We calculate the tail probability of the Q length and the waiting time using the discrete fast Fourier transform on the probability generating function that we found. Next. So now we have one example here, not about mean come later, but first we look at the tail probabilities. These are the tail probabilities of the Q length for the standard model with a mixed batch size distribution. One batch size distribution is Poisson, and the other one is geometric. So we can have very different distributions in one environment or the other. But this is not the random environment model, this is the standard model. We just take the mixture of these two different batch size distributions. One in Poisson, one. And here we see the Q length. You see, when the mean in both is the same, then that is this one, then you see very small tail. But when you differentiate, let's look at this extreme, one is mean is 6, and the other mean is 0.004, then we get a much heavier tail. And this is for the standard model. Now we go to the next slide. You see the same situation. These are the results for our complex model, which I analyzed in the last 45 minutes. And but it's interesting to look at the upper one, this one. These are tail probabilities. So go to the previous one again and look at the difference. You see? Jumps. You see? And this is at the level of probabilities. Probabilities are very small, but even you see that there is a large difference in tail probabilities. So that justifies our conclusion that you cannot take just the standard model with the mixed batch size distribution to get your performance measure for the random environment model, because already at this level you see that. Next. This is next.
Yeah, this.
Okay, this is for other. Let's forget about that. Oh, this is for the waiting time. This is the same phenomenon, but now for the waiting time. Okay, next. Go. Here you see the mean. Here you have the random environment model. Here you see when the mean are both 0.32, then you don't see any difference. Here also the mean waiting time, you can check the little, of course, again. But if there's a large difference between the mean batch size in one environment and compared with the mean batch size in the other environment, so this is maybe rush hour and this is rush hour and this is the quiet period, there's a lot of difference, then you see that the mean Q length here is 85 and here it's only 78. And for the waiting time you also see a very large difference. Okay, next. Okay, this is just for some other distributions, but the same phenomenon, so we can now slowly go down again. Here you see again it jumps up. Waiting time again jumps up. You see the same phenomenon. Now here the mean. Now we have constant and geometric. Then you see again these differences. It's the same phenomenon. It's only some other numerical something. Next. Lastly, we changed geometric and Poisson. First we had in one environment Poisson and the other geometric, and then we interchanged that, and then the tail probabilities were much and much larger. It has to do with the fact that a geometric distribution has, when the means are the same, the variance is larger than the variance of the Poisson if the mean is at least 2. Okay, everybody can calculate that. So we have heavier tails here. Next. Goes up again. Last one. Next is waiting time. Okay. And here you see enormous differences here. Well, enormous, not so, but much larger values. And that has to do with the fact that the variance of this mixture is also large. Next one. So it's now some conclusions, and then I think we can end. So for the random environment, late arrival system with delayed access and the random environment, we have given explicit expressions for the generating function of the Q size, the steady state Q length distribution, and for the probability generating function of the steady state waiting time distribution for an individual customer. And it's important, individual customer. Using the discrete fast Fourier transform method, tail probabilities will have been calculated, and using these tail probabilities, we approximate the long-run average Q length and the long-run average individual waiting time. And these results were very, very precise. We compared the numerical results of the standards model with the mixed batch size distribution with the numerical results of the random environment model. And we found that the standard model, and this is the most important conclusion, the standard model cannot be used as a reasonable approximation for the random environment model. That's the message I gave already in the beginning, and I want to repeat here. Next. Especially in case the mean batch sizes are very different, the two environment states, the discrepancy between the standard model and the random environment model is significant. That's one. If the mean batch sizes are more or less the same, then you don't see so much difference. But of course, a characteristic of rush hour is that these mean batch sizes during rush hour and the mean batch size during the quiet periods are very different. Hence, detailed analysis of the random environment model is required to get a correct insight into the idiosyncrasies of the model. an approximation with a more simple standard model with a mixed data is far from being acceptable. I pronounce it a little bit in a polemic way, but that's the message I want to get through. That's what I also said in another occasion. Mathematicians have the possibility to study rather complex models. I started from a theoretical model. Of course, if you start from an application and you are an engineer, of course, then you want to say, okay, this is a model which more or less does it. But then you can make very big mistakes. Okay, I think that's it.
Thank you so much. So actually, can I start questioning? Yeah? So first, I would like to know if this kind of distribution that you introduced, so mostly you get this difference between the results when you have very kind of skewy distribution. So maybe, can we call it a kind of a bursty traffic?
Yeah, of course. I really forgot. I could have given my introductory remarks in the form of, well, in internet traffic we have burstiness. Mm-hmm. And this is one way to start to get some insight in burstiness. That's it.
So because it looks like this, yeah?
Yeah, it is
for a short period.
I just forgot to use the term burstiness.
Okay. So and the second question actually about this interesting point about the zero at this z point or z star.
Yeah.
So what is there any intuition, because you had this the transform so the generating function at this specific point of the service time had a zero, like that. So was there some intuition behind that? So can we explain it?
No. It's the same if you look, for instance, at the GI and 1Q. Everybody has learned about that model in these introductory courses on queuing theory, where you know that also you need some omega in the interval 0, 1, and then the something like I don't know, something like this is the generating. This is the probability that the Q length is J. So then also you can ask yourself, well, does this omega have some intuitive meaning? Well, I don't know. If everything, more or less, Joshua would say, a philosophical remark, if every mathematical result would have an intuitive explanation, then we don't need to do mathematics because we just use our intuition. We get already the results. And so that's the richness of mathematics, that you find things which are new for which you don't have any intuition.
Can you explain the difference between standard model in terms of functions? Because I saw in terms
So please, you can go back to the
somewhere.
More. Here, these are explicit results for this standard model. And there you see
what is standard model?
What does standard model mean? That's what you guess.
One word.
Standard model. Well, let's say. Let's do it. But let's do it in continuous time. I have an MG1 model, I call it the standard MG1. But now I enrich this model in the sense that I have two arrival streams, and these arrival streams depend on some extra environment. What I mean in our comparison with the standard model is that we took here this weighted average, and we took again the standard MG1Q and fed it with this mean, this average, weighted average. So these are the formulas for the standard model. What the standard model means, you have no environment change, you have just one arrival stream.
This is the mean arrival.
And here I took the standard model with a very specific generating function for the batch arrivals. Of course, there is only one distribution for the batch arrivals, and I take the mixture of those two different batch size distributions in my environment model. But I can mix, so it looks as if you think, what is really the difference between the environment model and the standard model? Because also in the standard model, in the environment model, the mean arrival, the mean batch size arrival is also this previous one that Alexander?
Yeah, I understand.
It's clear?
Yeah.
Okay.
Because you mix two.
I think I mixed, yeah.
But I saw with right expressions here. I don't understand.
Yeah.
If you use previous expression
Yeah.
from different environment.
Yeah. Okay. More questions?
So if no, then we have a short break, let's say 10 minutes break, and then we come back to our session. Thank you once again.